So shall we start the session, sir? Deepak, sir?
Yes, sir.
Okay. Good evening to one and all present here. I would like to welcome you all for the fourth day ATAL online FDP on the topic Technological Advancement in Manufacturing and Industry 4.0. On this momentous occasion, I would like to invite our first session chief guest, Dr. Deepakkumar sir, Assistant Professor, Senior Grade, Department of Thermal and Energy Engineering, School of Mechanical Engineering, Vellore Institute of Technology, Vellore. He has published more than 30 research papers indexed in Web of Science, Scopus Index journals. Despite being his busy schedule, he has given consideration for our FDP. Once again, I welcome you, sir. I will hand over the session to our today's.
Shall I proceed, sir?
Yes, sir, you can proceed, sir.
Yeah. First of all, very thank you to Mr. Prabhu, the co-coordinator of this ATAL FDP, for giving a nice introduction. And I want to express my thanks for giving me the opportunity as an invited speaker on the FDP titled on Technological Advancement in Manufacturing and Industry 4.0 for the coordinator, Dr.G.Mahesh, Professor and Head, and the co-coordinator, Mr.M.Prabhu, and the Department of Mechanical Engineering, JCT College of Engineering and Technology, and the management. So I hope you participants, you could have got an experience on the last 3 days regarding the brief idea about Industry 4.0. So my today topic will be on the role of computational fluid dynamics in Industry 4.0. Some of you may be new to the topic computational fluid dynamics, and some of you may be familiar with the term computational fluid dynamics. So how this computational fluid dynamics plays a vital role in industrial research and product development, that will be focus of the today topic. Am I audible, sir? Can I move further?
Yes, sir, audible, sir.
Yeah, fine. So the presentation contains so a brief introduction to computational fluid dynamics, because you are already aware about Industry 4.0, the basics and the fundamental key terms on Industry 4.0. So I'm starting with computational fluid dynamics. What is computational fluid dynamics? The basic questions coming into your mind, and that questions will be addressed in the upcoming slides. And after that, the various CFD applications will be focused, and the historical background and development of CFD, how it is evolved in the recent decades, and the importance of computational fluid dynamics in industrial processes, various industrial processes, and a brief idea about industrial revolution, particularly Industry 4.0, and empowering Industry 4.0 with advanced CFD, computational fluid dynamics techniques, and the recent technological advancement in computational fluid dynamics, and benefits of using CFD in Industry 4.0, and the challenges and the future prospectus, and followed by the brief conclusions. I hope my slide is changing, right?
The slide is not visible, sir.
Slide is not visible.
Yes, sir.
Now is it visible? So I have to
Share the screen as a entire screen, sir.
I have to share my screen, right? I think you have to make me as a presenter, right?
Yes, sir. Anyone can share their screen, sir.
Now my screen is not visible.
Yes, sir.
Okay. So Could you please update the current status, how it is?
Now showing your screen, sir.
Yeah, my screen is visible now.
Yeah, sir, visible, sir.
So the detailed outline I have mentioned. Yeah, so I don't want to repeat again. Now let us move to the brief introduction to computational fluid dynamics. So generally the common questions coming into your mind, suppose if you are new to CFD, what is CFD, what is computational fluid dynamics, and why we are using computational fluid dynamics, and when these computational fluid dynamics results are valid, and how finally how the computational fluid dynamics is working, what is the background of this computational fluid dynamics. These are the common questions will come into your mind. And finally, what are the various applications of computational fluid dynamics. So I'm going to address each and every questions for you. So first one is, what is CFD? Suppose if you're working on any engineering problem, the engineering problem can be considered yeah, and it can be solved in generally three ways. One is experimental method. You can do the you can find the solution, or you can go for analytical method, or you can go for computational method. So each and every method having its own pros and cons, so its own advantage and limitations. So say for example, in experimental method, if you're going, obviously it will consume huge amount of money and huge amount of effort, and your time will be the major factor. Obviously, the advantage of experimental method is that is a real-time method. We can completely believe on experimental data. Whereas analytical method, it will be mean for some simple geometries only, and it can be solved in some simple problems like one-dimensional problem and some simple regular geometry problem we can solve with the help of analytical method. In case of some complex geometry where multi-dimensional approach is required, and a very complex geometry, not irregular geometry, it's a irregular geometry and some complex geometry is coming into picture, and a number of physics are involved in the system, we cannot simply go with the analytical method. We have to move to with the help of computers. That is called computational method. So obviously, either if you are solving an engineering problem, either in analytical method or computational method, obviously that should be tested in real time with some experimentation. So then only people will believe whether your work is correct or not. So you can claim n number of designs through analytical method or computational method, but finally whether it is working out or whether it is feasible in real time application or not, that should be tested in real time experiment with some prototype fabrication. So these are the some like similarity and advantage and limitations of each method. Now our today topic is focused on computational method. So computational method, particularly computational fluid dynamics related work. So the subject deals with the predicting the solution of fluid flow problems, including heat transfer, mass transfer, and chemical reactions phenomenon by using numerical methods with the help of computer. So suppose if you are considering a CFD person, suppose any person who is working in computational fluid dynamics, you can see them as a either they will be working on CFD development or they will be working on CFD application. Means actually, if you are looking at this CFD, the concept computational fluid dynamics is evolved with the help of three major contribution of three major department. One is engineering department, another one is computer science department, and another one is mathematics department. Because the physics what you want to predict, that should be understand. So with the help of corresponding engineering concepts. So either fluid dynamics problem or heat transfer problem or mass transfer problem or chemical reaction problem or whatever the problem may be, the physics you should understand. So that concept can be understood by the particular engineering people. Say for example, mechanical engineer, in specific thermal engineer, or whoever it may be. So they will understand the concepts. So the corresponding equations, governing equations, what are the equations governing? So that can be understood. Whereas the equations generally will be in the form of a differential equation or integral equations. So that should be converted into form of linear algebraic equation to get the discrete point solutions. For that, we need mathematical department contribution. Say, for example, various numerical methods. Okay, and so the contribution from mathematics also another important point. And whereas once you getting the algebraic equation through some kind of algorithms, we have to develop a computer programming code. For that, the contribution of computer science people is also very important in the development of computational fluid dynamics. So if you are looking at a person who is working in the computational fluid dynamics development, they will be focusing on the kind of algorithm and the discretization schemes, various methods, numerical methods to solve the problems they will work. So their main focus will be how to reduce the complexity of the system and how complexity of the code and the algorithm and the quicker results and a better accuracy. So they will be focused on convergence rate of the simulation, everything they will consider. Whereas another set of people, they will be simply using the CFD as a tool. So they will use CFD as a tool and they will be focusing for their own application. Suppose if I am working on solar aerator, suppose if I am working on heat exchanger design, so simply I will use the CFD as a tool. I'm not bothering about what kind of background is running, what kind of algorithm is running. So what I'm emphasizing here, so there are two set of people you can see in computational fluid dynamics. One set of people, they will be working on computational fluid dynamics development algorithm, and another set of people, they will simply use as a CFD as a tool. So obviously the contribution from these three departments is a major one for the development of computational fluid dynamics. So I hope you understood somewhat the basics of CFD, who are the overall the contributor for the development of CFD and overall the user. So CFD application, anyone can use the software tool that can be used for many applications. And the next question is, why we are using CFD? Why we used CFD? Because we can simulate, we have the ability to simulate real as well as ideal condition problem. So real-time problem as well as if you are having some ideal condition, both the problem can be solved with the help of computational fluid dynamics tool and simulation-based design instead of built-on test. Suppose if you have an idea of design, some n number of designs may be coming into your mind. So in that design, which design will be feasible in real time, which design give better performance, which design will give low cost, low operating cost, or low manufacturing cost and manufacturing feasibility. So these and all deciding factor to choose the particular design of particular system. So in that perspective, so you can use CFD tool as a optimum to find the optimum design. So suppose n number of design is coming into your mind. So which design will be best? So to find the optimum design, you can use the CFD software and find the optimum design. That design can be going for fabrication and that will be tested in real time. So instead of suppose in your mind 10 number of designs are coming into your mind. So design 1, design 2, design 3, like that, design 10, up to 10 designs are coming into your mind. So instead of doing all the design in real time, you can do the optimum design, which giving best design on the basis of our requirement, either manufacturing perspective, feasibility, cost, or operation or efficiency. Any terms you can consider based on our requirement. So we can finalize one design. So that design will be going for prototype fabrication. So, and also it will reduce the total effort required in the laboratory. So if you are optimizing your design through simulation, so in laboratory that will reduce your effort. And the simulation of physical fluid phenomena that are difficult for experiments. Say for example, in IC engine combustion, internal combustion engine, so inside physics, the combustion physics is very difficult to see in experiments. It may not be visible or it may not be transparent to the users. So if you want to analyze such kind of in detail analysis, the computational fluid dynamics tools will be very useful for the experiment which is difficult in real time, whereas in experiment in a CFD simulation we can get the detailed information. So obviously the comprehensive information, each and every corners of the systems we can get the information about the system. Generally the information is nothing but what is the pressure inside the system, what is the velocity inside the system, what will be the temperature in the system in terms of thermal perspective. And this CFD will be, once you are started to utilizing the CFD as a tool, that will reduce your cost of fabricating a product. So that will reduce the overall cost of producing a product, because in the earlier R&D stage, we have to spend huge amount of money for the particular new product. So through the simulation based design, we can get lower cost for the particular product design. And the speed of operation is also quicker as compared to experimentation. So experimentation, you have to spend huge amount of money and effort and time, but in computational simulation you can find the best optimum design with the help of computer and high-end computer that will reduce your speed of reduce your time, and the working speed can be improved. And in case of teaching field, this computational fluid dynamics will be a companion tool for fluid dynamics and heat transfer and thermal engineering related problem. And it will generation of interest in fluid dynamics and heat transfer phenomenon among students. And in case of research, it will be act as a complementary tool to experiments and theory. So if you are doing some kind of experiments, and you can get very few information from the experiments, because you completely depends on some kind of instruments, some kind of equipment. So that will give some data. But in case of CFD, it will be act as a complementary tool. So with the help of very few data, you cannot go for higher data processing for the entire system. Whereas in CFD, you can get more number of data regarding the system. So it can act as a complementary tool and provide valuable flow field information that experimental measurements may not be able to provide. Because suppose if you are interested in measuring temperature or pressure or velocity, very few locations you may place the in the experimental setup. Whereas in CFD, wherever you want to get the information, all the data points you can get the field variables like pressure, velocity, and temperature. And in design and analysis, it can act as a cost-effective tool to run what-if scenario to arrive at optimum design. So already I mentioned it act as a CFD tool can be act as a best optimum tool to best optimum design to find the best optimum design. So out of n number of ideas, so if I'm changing this particular geometrical parameter, what will be the effect? So which particular parameter will be the significance of particular parameter will be more, and which particular parameter will have less significant. So you can easily find through this comprehensive information through CFD tool. And the next question, so suppose if you are doing some CFD simulations, so I'm getting some results. So whether the results are correct or not. So here I want to highlight the great scientist Albert Einstein's quote: "A theory is something nobody believes except the person who made it. But an experiment is something everybody believes except the person who made it." So this is a great quote by the great scientist Albert Einstein. Suppose if you are doing some simulation work, theoretical work, nobody will believe until unless if you are showing some experimental proof. So if you are saying, so out of 10 number of designs, I found this particular design is the optimum design. If you are saying through the CFD simulation, but obviously the people will expect whether the particular optimum design will be feasible, whether it is the predicted CFD results, whether it is coming in the real time or not. Once you are doing experiment only, people will believe. And moreover, if you are giving some CFD results, and that results, whether it is how the results are correct or not, how you can ensure your CFD results are correct with the help of some experimental validation, you can ensure your CFD results are correct or not. So you have to do some benchmarking, some problem you have to first complete the validation of your CFD methodology. Then only whatever the games you are playing with the designs of particular system, the particular results will be ensured. So your CFD methodology is correct and your CFD results also correct. How it will be ensured? Through some validation of existing work. So you can do. So the existing work, you may have a question on here. So if I'm doing validation of existing work, how it will be useful for me? So first of all, you are ensuring I am able to predict, I am able to reproduce the same results which is available in the literature through the experimental data. If it is experimental data, that is well and good. Otherwise, even if it is CFD data also, that is also secondary options. So once you ensure your CFD methodology and CFD results are correct, thereafter whatever the changes you are doing in geometrical, material or operating conditions, everything will be, your results will be correct and you can convince the people. And the next question, how CFD works. So the final question may be how the CFD is working. Generally, you have to understand the physical phenomenon of the particular problem. So if the problem involves fluid flow alone, what will be the physics in it? Whereas in case of problem with fluid flow and heat transfer, what will be the corresponding physics and corresponding equations? And suppose the problem involves physics, particularly fluid flow and heat transfer, and say for example combustion, what is the corresponding governing equations? Suppose a problem involves multi-phase flow, what will be the corresponding governing equation? A problem involves a phase change material, PCM, what will be the corresponding equation? So as a person, you have to understand what is the physics behind your particular problem. So which particular problem you are focusing. So what is the corresponding governing equations are there. In order to solve that equations, you have to understand the physical phenomenon of the particular problem. Generally, this physics will be represented in terms of mathematical formulation that will be in the form of governing equations called partial differential equation or integral equation. The governing equation will be in the form of partial differential equation or integral equation. So this partial differential equation and integral equation, generally it is non-linear in nature. So it is difficult to solve in direct. So we have to convert this partial differential equation or integral equation into solvable algebraic equation. This is called discretizing the equation. So the partial differential equation and integral equation will be discretized into algebraic formulation. So now solving this algebraic equation will be very easy. So with the help of n number of numerical methods. So and this algebraic equation solution will give the solution of pressure, temperature, velocity, and all other required data depends on the problem at each and every grid points of the computational domain. So finally, what you will get, the velocity field, the pressure field, temperature field, density field. Suppose if you are working on mass transfer problem, concentration, mass concentration, if you are working for multi-phase flow, the different phases, and the combustion, the different combustion products, everything you can get. So this is the background of CFD, how it is working. So this with this quick review of this CFD working, I'm just moving to the next slide. So here the general background equation I'm mentioning for the fluid flow and heat transfer. If you are looking at this equation, the first term is known as the unsteady term, whereas the second term is known as the convective term, and the third term is known as the diffusion term, and the final term is known as the source term. So this is a general equation which can be applicable for any particular, any kind of problem where you have to choose the phi value in an appropriate value. Say for example, if I want to use this equation for continuity equation, I have to substitute phi is equal to 1, then this equation will be reduced to continuity equation. And if I want to substitute phi is equal to u, then this equation will be converted into x momentum equation. And if I use phi is equal to v, this equation will be considered as a y momentum equation. So similarly for z momentum equation, and if I use, instead of phi, if I'm using h value, h is nothing but specific heat into temperature, so Cp times T, this equation will become energy equation. So I have mentioned only for fluid flow and heat transfer problem. So these equations, if you're looking at, this is in form of integral equation. So you have to convert this integral equation into discretized algebraic equation. So that is our background work in CFD software. So these algebraic equations will be solved with the help of numerical methods. So in this example, I am considering only fluid flow and heat transfer, where the corresponding 5 variables are mentioned here. In case of depends on your problem, the 5 values may change, and this is the general equation. So these equations will be solved with the help of finite volume based solver. In case of the n number of softwares are there, ANSYS Fluent, ANSYS CFX, and Star CD, and like HyperMesh and Converge. Yes?
So slide is not moving, sir.
Slide is not moving. I'm right now, I'm in page number 9.
No, sir. 3, sir.
Oh, sorry. Still it is in 3. It is in 3.
Yeah, sir. It's still in slide 3, sir.
Oh my God. Wait a minute. So what to do, sir? I'm moving, but why it is not moving right now?
Sir, no, right now it's not moving, sir.
Okay, 1 minute, 1 minute. So please confirm whether it is moving or not, because I already moved many pages. Then
PPT is not visible, sir.
better I will share this way. Now is it visible?
So PPT is not visible.
1 minute. Now please tell me whether it is visible or not.
So now visible, sir.
Which?
So slide number 2, sir.
So now
So now slide number 4.
very good. So you could have informed earlier. Anyhow, I moved all this content. Anyhow, I will share the PPT later. So can you get the information here? Slide number 4.
Yeah, sir.
Fine. And already I covered this, so I skip now. And what about this? Now it is moving.
No, sir. It's still in slide number 4.
Oh, then while I am moving, it is not moving to your screen. Now?
Slide number 7, sir.
Okay. Now I'm changing slide number 8.
No, sir. It's still in slide number 7.
Okay.
Now in 8, sir.
Okay. If I'm making slideshow, it is not moving. Now let me know which slide you are looking at.
Slide number 9, sir.
Okay, fine. Now it is moving, I think so. Okay, shall I proceed?
Yeah, sir.
Okay. Is it visible for you? Because if I'm opening in slideshow mode, I think it is not visible. Now I'm making in normal mode.
Yeah, sir. It's visible, sir.
Yeah. So this is the background equation so far I have discussed, and previously I discussed regarding the how CFD works, the various like process involved in the CFD flow diagram, and later on I moved to the background equation and the fundamental equations, continuity and momentum and energy equations. And if you are looking at any CFD software, these particular key features or components are very important in case of CFD simulation software. First, you have to make a geometry. So which particular geometry you are focusing? Say, for example, a system, the computational domain, you have to find which particular computational domain you are going to work. And the geometry may be a regular geometry or it may be an irregular geometry. And the geometry should be like made as a mesh. So it means you are going to slice the geometries into n number of pieces. So that is called a mesh. So n number of regular pattern or irregular pattern of mesh. Okay, so structured mesh or unstructured mesh. We can call it a mesh or grid. So the computational domain will be like split into n number of small finite control volumes. That is called a mesh. So the corresponding physics you have to understand. Say, for example, if it is a fluid dynamics problem alone, the continuity equation, momentum equation plays a role. Whereas in case of heat transfer problem, the energy equation will also come into picture. In case of solar radiation is involved, radiation model will be coming into picture. In case of multi-phase flow or combustion or any other species transport. So the corresponding equations you have to model. That model you have to include in the software. So the problem may be viscous problem or a non-viscous problem, heat transfer problem, radiation, multiphase, material properties you have to define. And the problem may be a steady problem or unsteady problem. If it is a steady problem, only boundary condition is sufficient. Whereas in case of unsteady problem, both initial and boundary condition is required. And in case of solver, it depends on the requirement. You may solve the problem based on steady solver or unsteady solver. And the precision, the accuracy level, whether single precision or double precision required. And in case of steady solver, you have to fix your number of iteration and you have to fix your number of time steps in case of unsteady problem. And relaxation factor and convergence limit should be set for the good convergence rate of computations. And various numerical schemes you have to choose for the better accuracy and quicker convergence of the simulation. Finally, the results, post-processing, what will be the results? Generally, the raw data which is coming out from the solver will be the raw data. Generally, if it is a fluid dynamics problem, only pressure and velocity will be the raw data. Suppose in case of heat transfer problem, pressure, velocity, temperature will also come into picture. Like that, if you are adding more and more physics, say for compressible flow problem, pressure, temperature, velocity, in addition to density also coming into picture. Say for example, chemical reaction in combustion. So in addition to that, many components like species, what are the species involved in the combustion, that data will be also coming, and that data will be stored in each and every grid points, so the data will be stored. So the data we have to process for engineering parameter called like drag, lift, and the pressure drop, Nusselt number. So these are the terms we are calling. So these and all the data which is derived from the raw data called pressure, velocity, temperature. These are the field data variables. So these are the general step for any CFD problem. So in a particular software, finite volume based software, if you are using, these are the general procedure you have to understand. And the final questions, we have seen what is CFD and why we are using CFD, where CFD and how CFD is working, and when CFD is valid. Many questions we have seen, but finally where CFD is applicable. So I have shown many pictures here, sir. Slide number 11 is visible.
Yes, sir, visible, sir.
Yeah. So I have shown many applications here. So in simple term, I can say where CFD. So wherever fluid exists, you can use CFD application. In simple term, I can say wherever fluid exists, you can use CFD. So fluid is nothing but obviously liquids and gases. So wherever the liquid and gases are exist in nature, you can apply the CFD concepts and you can explore the various physical information about the particular system. So here I have mentioned some industrial applications and other sectors like sports and medical sectors also. So like mechanical industries like aerospace industry, automotive industry, submarine industry, and electronic packaging industry, and HVAC, heating, ventilation and air conditioning industry, oil and gas industry, and sports sectors, how to optimize the way of moving our body in case of swimming or in cricket or tennis, the racket design and cricket bat design, ball, everything you can understand how the ball will be spin when you are making off spin or leg spin. So how the ball will be interact with the atmospheric air. So how this motion of ball will be getting with the help of the interaction between the ground and the atmosphere. And heat exchanger design. Heat exchangers are used in many industries, process industries, thermal power generation, many industries. Heat exchanger we are using. To design the heat exchanger also we can use CFD. And the combustion in internal combustion engines. So we can predict the combustion characteristics and like wind tunnel and cooling tower, thermal power generations, and like components like compressor, turbine, and windmill, everywhere. So you can see the applications of CFD. So in simple terms, wherever the fluid exists, you can use CFD software to get the information, to get the detailed information, to get the detailed data. What is the data? Pressure, velocity, temperature, density, all the data you can get. By getting all the data, we can use this data for further understanding about the system, performance, how the system is performing, whether it is performing in better way or whether it is moving in a correct direction or not. So the next one I'm moving to with this brief introduction of CFD, I'm just moving to the historical background and development of CFD. So the background, we have seen the equation, Navier-Stokes equations, that is a background equation for the CFD. Navier-Stokes equation is one special form of the momentum equation, which is developed in the earlier 18th century. And later on, the application of finite difference method in weather prediction by Lewis Fry Richardson is a pioneering work by using finite difference method for numerically we are predicting the weather. That is a pioneer work by Lewis Fry Richardson. And later on, the introduction of numerical methods, so that will makes the solutions further easier in terms of numerical methods. We are finding the better in stability of the numerical solutions through von Neumann and Richmeyer's numerical stability conditions, and we moved further better in the progress of numerical solutions. And later on, finite element method open up the solution for different complex geometry. And the rise of modern CFD was evolved in the year 1960 to 1970 by the development of simple algorithm, which is the pioneering work by Dr. D. Brian Spalding and Dr. Shohas V. Patankar, who developed the simple algorithm. So that simple algorithm is the backbone for the all CFD solver. So almost finite volume based method solvers, the algorithm is the backbone. And with the introduction of this algorithm, we solved many real-time problems, in industrial level problems, and the introduction of turbulence modeling parallelly in the 1980s, Lauder and Spalding. So we used many applications with the help of CFD tool. We used for many applications, the CFD tool was used, and in the current scenario, the high performance computing era, so with the help of this high performance computing, we are able to solve more realistic problem, and the turbulence model capturing is still challenging, and it's advanced research. And these are the development of CFD in various timeline period. And the importance of CFD in industrial processes, particularly in chemical and process industries. So, sir, my slide is visible right now. I'm just moving the slide.
Yes, sir, visible, sir.
Okay. Say, for example, various industries, the CFD plays a major role. In chemical and process industry, fluid dynamics is vital in designing reactors, distillation columns, and the pipelines. So, it will accurately understanding the fluid flow. So on these particular systems will be very useful to optimizing the reactions. So ensuring the efficient mixing and reaction rates in chemical processes. And the safety, also another perspective. So you can see preventing the issues like pressure drops or leaks in the system by CFD analysis. And energy efficiency system can be developed. So reducing energy consumption by optimizing the fluid transport across the chemical and process industrial systems. So another one industry is very important in aerospace and automotive industries, where both aerodynamics as well as HVAC plays a major role. The CFD plays a major role in aerodynamic structure of the vehicle. So not only aircraft or automobile, it is also used in submarines. You can find the hydrodynamics of the structure. So efficient design. Suppose if you're having a better design for the like aircraft wings or any active or passive control of this lift. So if you're able to control the lift motion, so lift is nothing but upward force acting on the body. When the vehicle moves in the horizontal maneuver, how the force is acting on the body, that is a lift force. So lift force is a very important factor in case of aircraft design. Whereas in automobile sectors or submarines, so the drag will be acting as a important role. So both this drag and lift plays a major role on fuel economy. Okay, so maximizing the drag and maximizing lift for aircraft and automotive vehicles, leading to better fuel efficiency and performance. And in another aspect, the thermal management. So cooling of an engine. So how efficiently you are able to cool the engine, that will that will enhance the lifetime of the engine, so that the operation characteristics can be improved, and the prolonged operations we can get, and the lifetime also can be improved for the engine, as either aircraft or automobile or whatever the engine may be. So effective cooling is another kind of key research in using CFD. So what kind of cooling system will be very efficient for the better operation of particular system called engine, and that is applicable for any kind of automobile. And the another one sector is oil and gas industries, where pipeline design and safety, in case of oil and gas industries, predicting and managing flow rates and pressures to avoid leaks and ruptures. And we can recover more extraction of oil and gas in case of oil recovery system, optimizing the fluid injection process to maximize extraction of oil and gas. And the another sector is energy sector. So in a renewable energy system or a conventional way of producing energy or cooling system for power plant, whatever it may be. So I already mentioned heat exchangers can be found in many applications. So in energy sectors, the renewable energy, you can see wind is one kind of energy, and another one a kind of renewable energy, solar energy, and hydel and tidal power plant. Many renewable energy systems, you can see either air or water will be plays a major role. So in this, or gases will plays a role. So geothermal power plant or whatever the plant may be. So either renewable energy systems or a conventional way of producing energy through natural gas or coal power plant or any other petroleum based power generation sectors, whatever it may be. So energy sector, the CFD plays a many role in each and every component where the fluid exists. So already mentioned, so wherever fluid exists, the CFD application you can find either in a liquid or gaseous format. So generally, air, water is a very common fluids. And apart from that, lubricant oil, petroleum product, so refrigerants, so many fluids are available in the industrial processing system, industrial systems. So you can apply these CFD concepts. So it will be very useful for understanding the physics of the particular system and improving the system performance. And another one important industry is manufacturing and material processing industries. So in case of, so particularly in specific, the spray coating and cooling systems of any manufacturing component. So CFD plays a role, how faster the rate of cooling or how slow the rate of cooling. And in case of coating industries or spray coating industry, ensuring the uniform application of coatings, and mixing and pouring industries, pouring processes, so optimizing the flow of material to improve the product quality. So the CFD plays a major role. And another kind of industry is heating, ventilation, air conditioning, HVAC systems and environmental engineering. So efficient HVAC systems and pollution control can be done using the CFD software tools, and the proper ventilation, heating and cooling, improving the energy efficiency and occupant comfort can be ensured with the help of CFD predicted results, and designing systems like scrubbers or filters to manage and reduce pollutants in industrial effluent streams. So such a way the environmental hazards can be reduced. And another one industry is biomedical industries, where you can see the medical devices. So improving the performance of the devices like heart pumps and ventilators. In the recent years, we are this is another one outstanding growth of CFD application in medical sectors and biomedical sectors. And drug delivery systems, the designing efficient system for drug delivery via blood flow, these and all, and pumping, blood flow analysis, and these and all some of the applications of CFD in biomedical sectors, biomedical industries. So up to this, we have seen many CFD applications and the basics of CFD and how it is relevant to various industrial applications. And now let us see a brief idea about, already you could have seen this in Industrial Revolution, already you know the stories. Anyhow, I'm not going to take in detail. So the Industrial Revolution starts from Industry 1.0, also known as the first Industrial Revolution. It was the period when steam engines were first used in manufacturing and transportation. It began in the late 18th century, and whereas in the second Industry 2.0, also known as the second Industrial Revolution, for a period of rapid industrializations, and we can simply call it as electrifications, where the development of assembly line is formed. And Industry 3.0, so this is generally called as automations. It's also known as third industrial revolutions. Yeah, it was developed in the late 20th century, and with the help of computer automations were developed, and digital technology were used. And right now we are in the industry 4.0. This is known as fourth industrial revolutions, known as digitalizations. So in the terms this industry 4.0 use of advanced technologies to automate and intelligence manufacturing processes. It involves the use of technology like artificial intelligence, the Internet of Things, and big data analytics. And Industry 5.0 is a vision of our industry that focuses on sustainability, resilience, and human well-being. Set of technologies that builds in Industry 4.0, but with greater emphasis on collaboration between human and machines. So it is called personalization. And Industry 6.0 is a concept for the next phase of manufacturing. It's known as customization, which uses artificial intelligence and other technologies to create smart factories that can operate with minimal human interventions. So we were doing many customization in Industry 6.0. Right now, the key concepts or key components in Industry 4.0, you can see system integration, Internet of Things, and cyber security, cloud computing, additive manufacturing, and augmented reality, big data, and autonomous robots. These are the key concepts of Industry 4.0. And the circle I have highlighted, simulation, also plays a major role in Industry 4.0. So CFD belongs to this category. We are doing CFD simulation for the R&D, research and development for the particular industrial product and the process systems. So we are using these CFD simulation softwares. And I don't want to repeat this Industry 4.0 key terms. I just keep these two slides, and now I'm moving to empowering Industry 4.0 through advanced CFD. So the first one is smart manufacturing. So CFD simulations help in optimizing manufacturing processes by analyzing fluid flow and thermal dynamics. Sir, my slide is moving now?
Yeah, sir, moving, sir.
Yeah.
Right now you are in 25th slide, sir.
Sorry, 25th, yeah. So this leads to sorry. So this leads to enhanced efficiency and reduced waste and lower operating cost. And another key concept is product innovations. By providing detailed insights into fluid behavior and heat transfer, CFD allows engineers to innovate and design superior products, whether it is in the automotive, aerospace, or energy sector, whatever it may be. And predictive maintenance. With the CFD, it is possible to monitor the performance of machinery and predict potential failures before they occur. So this proactive approach ensures minimal downtime and extends the lifespan of the equipment, and the productivity can be improved through these systems. And sustainability, advanced CFD helps in designing eco-friendly processes by minimizing emissions and optimizing energy usage. This contributes to more sustainable and greener industrial practices. And customization, CFD allows for the simulation of various scenarios, enabling industries to offer customized solutions tailored to specific needs. This level of customization can enhance customer satisfaction and competitiveness. And integration with IoT. So combining CFD with IoT device provides real-time data and analytics, allowing for more precise control and optimization of industrial processes. And virtual testing, before any physical prototypes are built, CFD can simulate and test design virtually. So this accelerates the developmental process and reduces cost associated with physical testing. So as I mentioned earlier, instead of build and test, you can go for CFD based simulation. So simulation based design you can prefer. And enhance the safety by simulating hazardous scenarios. CFD helps in designing safer industrial environment and processes, reducing the risk of accidents. So safety aspects also CFD plays a major role. And the key technological advancement in CFD. So the era of high performance computing, so has dramatically increased the speed and accuracy of CFD simulation. So this allows for the analysis of complex fluid dynamics problems that were previously infeasible. Improved algorithms, so advances in numerical methods and algorithms have led to more accurate and stable CFD simulations. Techniques like larger simulation, direct numerical methods, Direct numerical simulations provide detailed insights into the turbulent flow. And cloud computing, cloud-based CFD solution enable access to powerful computational resources without the need of expensive hardware. Otherwise, you need to go for some hardware equipment for storing your data, and huge amount of data in a long time span of time. It will take a huge amount of effort and money. So the cloud-based simulation will facilitate this particular access. And machine learning integration. Machine learning algorithms are being integrated with CFD to improve the simulation accuracy and reduce computational time. So the integration of machine learning with the CFD software, so it will lead to better computational time reducing. We can reduce this hybrid approach leverages the strength of both the fields, machine learning as well as CFD. And multi-physics simulations. Modern CFD tools can handle multi-physics problems and simulating interaction between the fluid flow, heat transfer, structural mechanics, and the chemical reactions simultaneously. So we can solve the multi-physics problems with the help of high-performance computing or in a quicker manner. And real-time simulations. So advances in hardware and software have enabled the real-time CFD simulation, which are crucial for applications like virtual prototyping and the control systems and user-friendly interface. The development of more intuitive and user-friendly interfaces has made CFD tool more accessible to engineers and researchers, even those without extensive computational background. So user-friendly interface, so you can easily understand the way how to use the software in a shorter period of time. So open source softwares, the availability of open source of the softwares has fostered innovation and collaboration within the scientific community and allowing for the development of new methods and applications. So already I mentioned the CFD people, you can find either they will be working on CFD development or CFD applications. So these kind of open source softwares will be very useful for the development of CFD softwares because it is openly accessed for everyone in the world. So they can like understand the background of the software, what is the actual background is running behind the software, and those who are interested in the CFD development, they can understand and they can develop their own models for the betterment of better numerical accuracy and convergence and quicker computational time. So the benefits of using CFD in Industry 4.0, so enhanced efficiency, cost reduction, and improved product quality and faster development cycle. In case of CFD simulation in efficiency, CFD simulations allow for the optimization of processes leading to increased efficiency and reduced energy consumption. Cost reduction by identifying the potential user issues and optimizing designs before physical implementation. CFD helps in reducing cost associated with trial and error method and the physical prototyping. So I already mentioned simulation based design instead of built and test. So simulation based design will reduce your effort in experimentation. So n number of design, out of 10 designs, which design is best, you can choose the particular design that only can be fabricated in real time. So the improved product quality, CFD provides detailed insights into fluid dynamics and heat transfer, enabling the design of high quality products with better performance and reliability. So the product quality can be like assessed with the help of simulation and which particular product giving better performance in terms of efficiency or in terms of operating conditions, whatever it may be. So you can improve the quality of the product and faster development cycle. So virtual prototyping and simulation speed up the developmental process, allowing for the quicker iteration and time to markets. So generally we people engineering, we are working on either the existing development for the existing design, or we will go for some development of new product. So these are the two major focus we are doing in R&D. One is developing the performance of existing product, or you are going to develop completely new product. So for both the cases, this CFD simulation tool will be useful and the faster development cycle you can attain. And the benefits of using CFD in Industry 4.0. So other terms, if you're including considering predictive maintenance, customization, sustainability, risk mitigation, and data-driven decision making. And CFD can predict wear and tear in machinery and enabling proactive maintenance and minimizing downtime. And the customization, CFD allows for the simulation of various scenarios, enabling industry to offer tailored solution to meet specific customer needs. So what particular case you want to analyze or identify, that can specific problem can be solved with the help of the CFD simulation software. And sustainability, by optimizing energy use and reducing emissions, CFD contributes to more environmentally friendly industrial practices. And risk mitigation, CFD helps in identifying and mitigating risk by simulating hazardous scenarios and ensuring safety in industrial processes. So wherever you want to do experiments where the hazardous is human hazardous is more, there you can use the virtual simulation that will give better prediction of the particular phenomenon, that will reduce the risk of human hazardous. And data-driven decision making, integrating CFD with IoT and big data analytics provides a real-time insights, enhancing decision-making process. So based on the CFD results, the data will be processed, and so in a sequence of operations, so you can easily plan the operation time and operation period, the cycle of each and every product life cycle. Wait a minute. So the challenges of CFD in Industry 4.0. Now, let us focus on the various challenges involved in CFD for Industry 4.0. One is computational resources, and another one is complexity of the models and data management and integration with other systems and the skill gap. So these are the major challenges we are facing in CFD for in Industry 4.0. One is computational resources. Obviously, high fidelity CFD simulation requires significant computational power, which can be costly and resource intensive. In all industrial level problems, it needs very high-end computers, whereas in case of academic level fundamental research, we can go with some low-end configuration, but all industrial processes involves huge number of elements, finite volumes, so that requires more computational power. And the complexity of the model, so accurately modeling complex physical phenomena such as turbulence and multi-phase flows, and still it is a challenging task for many researchers who is working in the CFD development for the particular applications. And data management, handling and analyzing the vast amount of data generated by CFD simulation can be overwhelming. And integration with other systems, so seamlessly integrating CFD with other Industry 4.0 technologies such as IoT and artificial intelligence requires sophisticated software and hardware solutions. And the skill gap, there is a need for a skilled professional who can effectively use CFD tools and interpret the results. So if you are if you are an end user, if you are using a CFD tool, anyhow you should know the background of CFD, then only you can effectively utilize this tool. As I mentioned earlier, the CFD people, one is working on CFD development, another one simply using CFD as a tool. So even though we are using CFD as a tool, we should understand the background of the CFD, then only you can effectively utilize the tool for the particular physics and particular model or particular system. And the future perspective of CFD in Industry 4.0, and so advancement in HPC, high performance computing, continued improvement in high performance computing will enable more accurate and faster simulation. Machine learning integration, combining CFD with machine learning will enhance simulation accuracy and reduce computational time. And multi-physics simulations, future CFD tools will handle more complex multi-physics problem, providing even more comprehensive insights. Cloud-based solution, the adoption of cloud-based CFD solution will make advanced simulation capabilities more accessible to a wider range of industries. And real-time simulations, advances in real-time CFD simulation will be crucial for applications like virtual prototyping and control systems, and user-friendly tool. And development of more intuitive and user-friendly CFD tool will make them accessible to broader audience. So sustainability focus, future CFD application will increasingly focus on sustainability, so optimizing processes to minimize environmental impact. So now I want to come to the conclusion of my presentation. So the computational fluid dynamics is a pivotal technology in the evolution of Industry 4.0. It provides powerful simulation capabilities that enhance efficiency, innovation, and sustainability across various industries. The continuous integration of CFD with other Industry 4.0 technologies like IoT and AI will unlock new possibilities and further industrial transformation. By enabling optimized processes, predictive maintenance, and customized solution, CFD is driving industrial transformation and helping industries achieve higher performance and reduced environmental impact. So CFD advancements are pushing the boundaries of what possible with the CFD, making it an even more powerful tool for industry and research. So while CFD offers numerous benefits, there are also challenges that need to be addressed to fully leverage its potential in Industry 4.0. Despite facing challenges such as high computational demand and the complexity of models, ongoing advancement in high-performance computing, machine learning integration, and cloud-based solutions are addressing these challenges and paving the way for more accessible and accurate CFD applications. The future of CFD in Industry 4.0 is promising with potential for real-time simulation, improved user interface, and a greater focus on sustainability. So after this, I want to conclude my presentation. Now I just show my textbook which I'm referring for CFD. If you're interested in CFD computational fluid dynamics, you can refer this textbook. These textbooks are more than sufficient for understanding the computational fluid dynamics background, concept, fundamentals. So the Westick, HK and Mahesh Segra, this is a textbook which is focused on introduction to computational fluid dynamics based on finite volume method. So finite volume based method approach is described very detailed in this textbook, first textbook, and the second textbook, J.D. Anderson, Computational Fluid Dynamics, the Basics with Application, McGraw-Hill Science. So these textbooks focused on finite difference method. This is a textbook. If you're following, you can understand the finite difference method of approach, how to solve the CFD problem. And Patankar, S.V. Patankar, as I mentioned earlier, the pioneer work from S.V. Patankar and Spalding, they developed the simple algorithm which is used in many CFD software, finite volume based software. Most of the software, they are using this finite volume based solver, simple algorithm. So this algorithm is used to solve the background equation of CFD like Navier-Stokes equation, continuity equation, momentum equation, and energy equations. So this textbook you can refer to understand the simple algorithm. What is simple algorithm? How this algorithm is used for solving the CFD based problem. And Muralidhar, Dr. Muralidhar and Dr. Sundararajan, computational fluid for heat transfer. You can further understand the computational fluid dynamics problem and heat transfer problem in depth for specific cases. And I want to highlight one more textbook, Atul Sharma, in the recent years, 2016, the book was published. It is completely physics-based approach, not a mathematical-based approach. Suppose if you're feeling I'm not good in mathematics, I want to understand the CFD, but I want to use the software effectively, you can go with this book, Atul Sharma. Dr. Atul Sharma is a professor from IIT Bombay. He wrote a book, Introduction to Computational Fluid Dynamics Development Application Analysis. So this book's completely based on physics-based approach, not mathematical, complete mathematical. It is not complete mathematical, it's completely physics-based approach. So whoever feeling low in mathematics, you can go with the book. You can definitely get more interest on the computational fluid dynamics course and the research. And the publications, some of the publications I referred related to CFD and Industry 4.0. So I have listed here. And these are my publications, some recent publication I have highlighted. Most of the papers I have worked in CFD software as a tool. So I'm working on computational fluid dynamics, flow over and external flow and flow over structures, particularly external flow, block body flow analysis, heat exchanger design, and renewable energy, and phase change material, thermal energy storage, and solar aerator. So these are some of the areas I'm working right now. So if you are interested, you can give a mail to me. That is in the very first page. I will show you my first page. You can contact me for any future research collaboration if you are interested in CFD applications. So with this, I want to complete my presentation. Thank you for all your kind attention.
If participants have any doubt, you may ask.
If you have any basic questions regarding computational fluid dynamics or any basic fundamental questions related to research, how the CFD softwares are used in R&D sector, you can ask a question. I'm ready to answer for that. I'm very happy to share my experience.
Good evening, sir. Deepak sir, Dr. Deepak sir.
Yeah, yes.
Sir, I am Sivakumar from Indonesia.
Yes, sir.
I have one small doubt, sir.
Yes.
In the heat exchanger,
Yeah.
there is an outlet pipe.
Yeah.
That pipe is more erosion due to seawater.
Okay.
So, is there any relationship between the flow and the corrosion takes place duration is any relation like that, sir?
Yeah. So your question is the outlet pipe of the heat exchanger is exposed to open environment. Am I right?
It is like no, sir. It is closed with it open only. Yeah, open only. Yeah.
So open environment. The pipe is exposed to open environment. The air particles, like in the suppose the pipe is exposed to open environment, the water particles which is in the air may contact with the pipe surface. So the particle may be suspended over the pipe surface, and the corrosion rate you are in you want to find, right?
Yes. Yeah.
So how it will be corroded? So this kind of reactions rate also you can find with the help of CFD software. Yes, you can find. You have to use the appropriate model. So the chemical reactions, how the layer you have to consider, the thickness of the material you have to consider, and the corresponding model reaction you have to consider. With the time progress, how the rate of penetrations, like the corroding material will be. That analysis you can do in CFD, sir.
Okay. So is there the flow pattern is like a turbulent at the beginning of entry of a fluid. Inside the pipe, it is seawater only. It flowing like a.
Your first question is over.
Yeah, the same question only, sir. I asking you about the flow entry level. When we visualize with our CFD analysis, it's like a turbulent. Then after a certain distance, it become laminar. So this turbulent, is there any connection for this erosion? Again, no, right?
So you are talking about the turbulent in the flow. It is happening inside the heat exchanger, but corrosion you are talking about outside or inside?
No, inside only. Erosion, not corrosion. Erosion, because of seawater.
Okay, not corrosion. Okay, material eroding.
Yeah.
Oh, okay. So material eroding, that is inside the heat exchanger.
Yes. Yeah,
so
that pipe, only the exit pipe of the heat exchanger.
Exit pipe, but inside surface. Am I right?
Inside surface, yeah, correct.
Okay. So now you
exactly
can
the weld joint. The pipe is connected with the bolt. That weld joint, it is only corroded. Eroded.
Yeah, I understood your problem. Now only I understood your problem. I thought that's what I'm asking. It is open environment or inside pipe? That's
no. Inside. Yeah. Sorry.
Okay. Inside pipe means so you can easily correlate. You can correlate this phenomenon with the help of skin friction coefficient in fluid mechanics. There is a factor called skin friction coefficient. More friction of fluids over the surface, that will make more erosion. Am I right?
Yeah. Yes.
So where the friction is more, you can easily find with the help of CFD software. Where the skin friction coefficient is more, you can identify the location first. After identifying the location, so how we can modify the fluid flow inside the system such a way the skin friction coefficient can be reduced. That will give the less effect on erosion. Such a way you can go for long lifespan of the system.
Yeah. Okay.
Are you getting my point?
Yes. So whether anything correlated with the welding process is the reason for this erosion? Only welding zone it is affected more.
Yeah, that's what I'm asking. Corrosion is something different, erosion is something different. So corrosion, that physics is something different. Now if you are focusing only on erosion,
yes.
You have to focus only the skin friction coefficient of the material.
Okay,
so that skin friction coefficient is predictable by the CFD software.
CFD software. Okay, right. Okay, sir. Okay. Yeah, I got it. Yeah. If anything, I will contact you, sir.
Sure. I have given my mail ID at the beginning of my presentation.
Sure.
You can contact. I'm happy to collaborate with you in future. Suppose if you're interested.
Yeah, sure. Yeah. Okay, sir. Yeah. Thank you, sir.
Yeah, welcome.
Any other participants?
Sir, my screen is visible, sir?
Yes, sir, visible, sir.
Title page, na?
Title page, sir.
Okay. So the audience can take my mail ID and my contact number. They can contact me later also.
Thank you, sir, for your valuable speech towards this topic. We learned so much from your topic, sir.
Yeah, thank you so much for the opportunity. Once again, I thank the department and the coordinator and co-coordinator of JCT College of Engineering, Department of Mechanical. Thanks for the opportunity. Thank you.
Thank you, sir.
Yeah.
Participants have to wait. The second session will start soon. The resource person will join soon. On this momentous occasion, I would like to invite our today's second session resource person, Dr. Dinakaran, sir, Senior Technical Manager, Research and Development, Center for Excellence Robotics, HCL Technologies, Chennai. He has a vast experience in the field of robotics and its technology. Despite being his busy schedule, he has given consider for our FDP. I welcome you, sir. I will hand over the session to our resource person, Dr. Dinakaran, sir.
Yeah, thank you, Prabhu. Thank you for the nice introduction and invitation. So, first I would like to thank the management of JCT College of Engineering and Technology and Dr.G.Mahesh, Professor and Head of the Department of Mechanical Engineering, and the coordinators of this program, for invited me to deliver a lecture on this great FDP. Really, it provides kind of enthusiasm to meet all the members who are interested in manufacturing and AI, and to meet many faculty members, industry members who have participated in this program. Then I appreciate all the participants who are showing interest towards this, because it's picking up slowly. And if you could see, the industry is adapting Industry 4.0 and AI kind of models in all the process. And I think it's the right time to organize such workshops to enrich our capabilities towards the new trends, towards the new opportunities. So whenever the industry is changing the scenario, that reflects in academia also. But actually it should be in reverse, that normally the universities will do the research and they publish and they bring it in the academics, and then it will be disseminated to the industries. Then it will go as industry practice. Again, that will reflect to the academic institutions. Thereby the tuning will happen. This is how the CIPs are there in Europe and US. But here, first it is coming to industry, and then it is going to the academics, right? But I think this is the right time that the JCT College of Technology, they've taken initiative to educate the academia on how the industry is changing, because manufacturing is one of the areas where the India is flourishing. So it supports a large extent in the GDP growth. So in the sense, the factories are changing, the manufacturing process are changing. How it is changing, how it is shifting from the basic setup to smart industries. So that's very much required to understand and adapt towards the changes, both in the practices and in academia. So in that way, once again, I appreciate all the members who are participating in this program. So just I would like to throw some lights on where we can use AI. Please permit me to share my screen. Prabhu, is it visible?
No, sir, it's not visible, sir.
Not visible.
Yeah, sir.
Actually, I shared it. Cannot share your, okay. Visible?
Yeah, visible, sir.
Visible. Thank you. Yeah. So in this FDP, I would like to focus on intelligent mission tools. How the mission tools are transformed after introduction of AI in this. I hope that many of the sessions you had, participants, may you please respond that what are the sessions you had related to manufacturing, anything?
The topic related to manufacturing and the Industry 4.0. What are the technologies that are involved in current scenario, sir?
Oh, okay. Industry 4.0 technologies. Okay, okay. Okay. I think about the automotive industry, how they are using some smart manufacturing,
Yes, sir. Yesterday,
Uh-huh.
we discussed with the how the FEA has been used in Industry 4.0 in HAV.
Okay.
That's all we have discussed yesterday, sir.
Okay, okay. Thank you. So 1 second, I just changed the layout. It's visible now, right?
Yeah, visible, sir.
Yeah, okay. Okay, so already there were some discussions happened. Okay, hope that many of them started understanding the scenario. So my area of discussion is very limited to the intelligent machine tools. How we can apply the artificial intelligence models, AI techniques in the machine tools. I can discuss one case study on this, how we can model some of the parameters and how we can make use of those models for taking some decision. Okay, so in depth study on that one, I would like to discuss one thing in that. Then apart from that, in overall, in my perception, how the industry is moving from the industry 4.0 to the AI-based industry 4.0. So how that scenario is changing, what are the areas to focus, and where we are going to apply these algorithms, and how the future is going to change. All those things I would like to cover. Maybe it's a very short time, but I will limit my discussions with these topics only. So everybody knows that the industry 4.1 started with mechanization, water power, and steam power. Everybody is aware of participants. May please mute. Yeah, thank you. So the mechanization, water power, steam power is industry 4.1, and then it is moved from industry 4.1 to 4.2, mass production assembly line. When the electricity is introduced, okay, industry 4.2 is introduced in the factories. Then when the computer and automation is introduced, industry, we call it as industry 3.0 revolution. When the cyber physical systems, robotics are introduced, we call it as industry 4.0. This is how it is moving. See, in industry 4.0, we can call it as the artificial intelligence in the manufacturing. We can call it as data current. I think one of the founders, I forgot his name, he coined it, the AI is like a data current for the factories. What kind of revolution happened when the electricity is introduced in the factory? The same kind of revolution, the same kind of transformation is going to happen in the industries. That's why he is coining like it is a data electricity. It is going to change the entire industry. So when you are comparing the transition from 3.0 to 4.0, I told you about a 3.0 is computer and automation, and industry 4.0 is cyber physical system. Have you come across this slide anywhere? Any participant? So how the blend is happening, how the synergy of domains are happening, and how it is changing the systems levels or technology level. If you see in a y-axis, basically in the 90s, 95, the mechatronic term is introduced by Japanese industries. They introduced electromechanical systems, and they introduced a concurrent approach in the design, where they combined the electrical systems, electronic systems with the mechanical system. So it's kind of synergy happened during that time, 90s and 2000, that time. Then after that, the control engineering and embedded systems, automation, software engineering, and then computation, all those things are combined with these basic electromechanical systems, and they formed cyber physical systems. We call it as, what to say, it's a kind of industry 4.0 revolution. Okay, so where the robots are introduced, cars are moved from basic mechanical to electronic oriented automotive thing. I think many of the discussions happened in this FDP also about how the transformation is happening in the automotive sector. Many things are converted into electronics, right? Electronics and the smart thing. But the electronics, embedded systems combined with the automotive sector, that is bringing mechatronics based systems, cyber physical systems in the automotive thing, right? So medical devices, there is a 180-degree shift in the medical device. So where previously medical devices, say for example, if you take BP monitoring, okay, normal manual based instruments are available now. Everything is automated, just press it through pump, it can measure and can show, it can save the value. Those transformations happened during this cyber physical system revolution. It's Industry 4.0. Now, from the Industry 4.0, slowly the domain is expanding and it is moving towards maybe the next revolution. Still, the transition is happening because of the introduction of big data, artificial intelligence, cloud, and the data mining kind of things. They are combined with the different methods, different application systems. Like if you take home, okay, previously civil engineering is just civil engineering. Okay, civil engineers are dominant in the construction. But if you take smart homes, apartments now, see escalator system, elevator system, surveillance system, security system, the camera, all those things, building management system is a separate control room. It's like a factory to handle everything, right? So all those things are implemented in the buildings. Now the buildings are no more civil buildings. It's basically a smart building, we call it as. So similarly, smart transportation systems, smart grid, okay, then smart factory. Smart factory is the thing that we are going to see in detail. That's what we call it as smart manufacturing. So previously, it's a manual method, then automated method, robotic assisted methods, and now it is going to move towards AI-based methods. Okay, so when we are implementing those things, okay, when those algorithms and cyber physical systems, software systems, control systems into different applications, how that domain is transforming. Okay, so here you have seen different domains and how it is interacting and where it is applied. And now you can see how in technology perspective, the Industry 3.0 is changed to Industry 4.0. Suppose if you take Industry 3.0, so where we have a mass production, automated factories, there we use robots to do the operation, say for example. Now in Industry 4.0, so where we use the robot with the different capabilities. It is not just a robot that will do the repeated work. So we have defined that robot is used for doing a repetitive work, and that can assist a human being in some cases. Okay, wherever you find it dull, dirty, okay, so very difficult to do, those places we apply the robots. But how it is moved in Industry 4.0 is the robot itself is taking a decision, and robot itself is behaving like a human to take a decision on some of the controls. So that's how the factory is moving. That's why we call it a smart factory. See, Industry 3.0, it is automated factory, and we call it a smart factory in Industry 4.0. Industry 3.0 is a low-level integration. Industry 4.0, it is entire process integration. Say, for example, within the factory, the machines, the robots, conveyor systems, maybe the storage, inventory, those processes are interlinked in the Industry 3.0. But in Industry 4.0, everything is integrated. Even outside the factory also, outside factory activities also got automated. That's the importance of Industry 4.0. Entire process integration, this will say, nowadays you are very well aware that how the Amazon is handling the outside delivery or through drones, how they are doing that. So even outside the factory, how the automation is taking place in the logistics, okay, how they are tracking it, okay, how they are optimizing it. All those technologies are implemented. Not only the inside factory activities are automated or integrated, the entire process of the business is completely automated. That's what we call it as Industry 4.0. That's a transformation happening in Industry 4.0. Mechatronic systems, yes, of course, it's electromechanical system, but the cyber physical system includes intelligent algorithms to operate that machine and to take a decision by itself or to adapt for the environment by itself. Then in Industry 3.4, it's a fixed automation. Say if there is a product variation, immediately we need to change the entire setup, right? But in Industry 4.0, it's a kind of adaptive automation. So many models of the same product can be processed, can be manufactured in the same assembly line setup, because the machines are very adaptive, the systems are very adaptive. And Industry 3.0, where we have programmable automation, and here it is adaptive kind of automation. I already talked about the macro level integration. It integrates all the activities, including the enterprise resource planning. This ERPs are there for the inventory control and all those activities. Okay, when there is a component, okay, missing, you can find out. When the component is going low in volume, immediately you can order. All those things can be processed automatically. So that's what is the macro level integration happened in 4.0 scenario. Okay, so as I mentioned, yes.
Sir, I think your slide is not moving. Sir.
Now it's moving?
Sir, still in the first slide, sir.
First slide?
Yeah, sir.
Oh, sorry. I think I moved 3 to 4 slides. There is some issue. See, please inform me because 63 people are there.
Okay, sir.
Dr. Ramesh Kumar, any raising hand? Any questions?
So previous session they asked the question, sir.
Oh. Is it okay now? Is it changing?
So it's not showing, sir.
I don't know what is the issue. See, it's showing that an error occurred when sharing a screen. Please try again. See, anything you have to make me as a presenter or something like?
So anyone can access this link, sir.
1 second. It's not. Right?
Yes, sir.
Are you able to see? Are you able to see?
No, sir.
Now?
Now visible, sir.
Okay. Is this transition from 3.0 to 4.0, right?
Yes, sir.
Okay. Please inform. Okay, otherwise I'll be talking without showing this thing.
Okay, sir.
They'll be clueless. Yeah. So this is what I showed. One side is system level, another side the technology improvement, and how it is interacting or that synergy is happening. This slide I showed. And the next one. Yeah. So now the slide changed, right?
Yes, sir. Changed.
Yeah. Okay. This is what I explained. How the automated factory 3.0 to 4.0 comparison. That's what I explained. It's moving from automated factory to smart factory. Okay. So now come to AI in manufacturing. Where are the places there we can apply this AI for improving the manufacturing process? So there is a debate that if the AI is implemented, that will take away the jobs. The same thing, the same kind of scenario was there when the computers are introduced during 1995. The same thing happened when some kind of advanced algorithms or the kind of software is introduced. Okay, some automation software are introduced in the market. The same kind of argument, again, it comes because of AI, but it's entirely different. It is not like what was happened in 90s or 2010 or 15, but it's entirely different because we can call this as the AI era. because it completely changing the scenario of the factory. But it is going to induce many of the opportunities for the innovation and further improve the products, further improve the process. Okay, so the nature of the job will change. The nature of the job will change, but the job definitely it will create many of the jobs. See, if there is a welding, if 2-3 people are doing welding, when the robot is introduced, if they have one welding robot, okay, that will replace one person, but still one person is required to operate the robot. Similarly, here also, there would be some automation of repeated tasks, okay, but definitely there are some innovations, developments are required for the futuristic manufacturing. So for which the people are required who are very well aware of these technologies, who could innovate and transform the technologies. So if you take AI where it is used in this, if you take digital twins, how many of you heard about digital twins? Anyone? No idea.
Last 3 days we
Digital twin they talked about.
yeah, sir.
Yeah, good. So it's basically a virtual model that replicates the physical process. Digital twins in the sense, say, if you are having in manufacturing perspective, if you have a factory, that you can replicate it in the virtual environment, and what is happening there, same thing can be retuned and remodeled again and again. So thereby you can have a replica of real factory, some imaginary factory you could visualize. And if you like to change anything, if you like to modify or revisit anything, you can do it in the virtual thing and you can implement in the actual thing. So that's what the digital twin, that is really supporting the manufacturing process optimization. And come to a quality inspection. Quality inspection, vision systems are widely used in the factories. In the automated factories, previously they used the vision system for categorizing the product, for accepting or rejecting, kind of taking decision. They use the vision system. So they use a simple image processing algorithms. If you find any cracks or any holes, any dots, you reject the part. If not there, you can accept the part. We call it as template matching kind of algorithm that was used in the image processing. But what is the advantage of using AI in this classification in the sense? Whatever may be the product orientation, okay, whatever may be the angle of tilt of the product that is coming in the conveyor, whatever may be the lighting, illumination, okay. So irrespective of those conditions, AI algorithm can capture the output and it could easily classify whether it is defect component or it's a defect-free component. So that's the scenario in the industry. And if you take predictive maintenance, this is the area I would like to focus today, and how we can apply AI in the predictive maintenance or condition monitoring kind of algorithms. Okay, so predictive maintenance in the sense, the maintenance process, normally we know the scheduled maintenance, the breakdown maintenance. Normally we plan for every 6 months or 1 year, some interval, and we shut off the whole factory and do the maintenance process. But in the predictive maintenance, so based on the data that is available with us, many sensors, edge devices are connected to the process machines, all the equipments, devices, measurement devices everywhere, and all the data are acquired and analyzed, and where the fault is going to be. So those things we can diagnose, and before acquiring that problem, we can predict when it is going to fail and we can attempt that problem. So that's what is a scenario that's going in the predictive maintenance sector. And then if you take up robots, so there is a challenge in the implementation of robot in the industries is when you program it, when you program the robot, normally they use a kind of simulation environment or playback kind of program of robot for repeated task. Say if the part orientation is changed, how the robot will recognize. Say if you're handling some square cubical component, and when your gripper has to pick only 2 sides, okay, 2 sides, that consistently 2 sides, maybe if you have 4 sides, 1, 2, 3, 4, it has to pick 1 and 3 in the sense. It should not pick 3 and 4 because say if it is soft side, okay. So every time if there is a orientation or error, anything when coming in the conveyor, how we take that. Okay, those kind of intelligent algorithms are in place. Automatically it will see the shape and it can recognize the component, and automatically it can pick in the appropriate size. Okay, that is one. Number two, if you are having say 15 to 30 different components where the process sequences are different for each and every component. In the robotic operation, okay, in the industry 3.0 scenario, the robot will execute a constant repetitive programs. But in this scenario, what we can do with the help of vision system, what component is coming, what is the sequence of operations that needs to be carried out for that component with the machines or other equipment, that can be decided. Accordingly, the robot will change the sequences. Automatically it can do. Okay. Then another thing is when it is coming to the assembly line, okay, using the robot for micro, say if you take semiconductor industry assembly, say this mobile phone assembly, if you take, it's very minute thing, right? So where we can take help of the robot, robot will assist the human being for doing that work. In the sense, robot along with the human is working in the industry so that we can avoid many kind of bottlenecks in implementation of robots. When the sequences are very, very complex, okay, when the sequences are not connected in terms of technology or in terms of size or dimensions of the component. Say, if the robot is should handle a small screw and it has to handle 5 kg weight, in the sense, screw and this one, for both the things we cannot use the same kind of gripper design, right? So what we can do, we can ask the robot to do 5 kg weight, and whichever is less thing, that less effort required, that human being will take that screw and put it there. So like this, robot and the human are sharing the platform in doing that work. That's what we call it as cobots. So there are different standards for the cobots. Whatever the standards we used in the industrial robots are not applicable for this one because of safety issues. We have, there are 3 types of safety layers in the industrial robot, but in the cobots, okay, it complies with the standards so that human being unintentionally, if they are moving the arm or if they are going near to that when the work is doing, automatically it will recognize and it will stop. Okay, so those kind of intelligence are built in the robot when the AI kind of algorithms are implemented. Then the energy management, I hope that energy management is covered in the lecture. So where, say for example, completely if you like to automate the lighting system in the factory, the illumination level is taken, and the illumination level in each and every place is measured with the help of the sensors. And if there is any deviations in that, if it is up during morning time or afternoon time, and when it is going down after 6 o'clock or 7 o'clock, slowly the illumination control can take, so that how much lighting is required for the factory, that alone can be illuminated. Otherwise, consistently, if you switch on all the lights from morning to night, okay, energy consumption will be high. It's just example I'm telling. Likewise, we could optimize the kind of lighting system to the high-end blower or boiler kind of systems also. You can automate it. Thereby, huge energy saving is possible through this AI implementation. So basically, we are playing with the data. How much data available to us, when it should be switched on, when it should be switched off, when we should provide low energy, when we should supply high energy for operation. All those things we can play, and we can optimize the complete energy utilization. Thereby, we can achieve the energy saving, energy conservation. Yeah. So then the resource management. Resource management in the sense, maybe the persons applied for, assigned for the jobs, maybe the resource in the sense, employees assigned for each and every job, that you can optimize it. Okay. So in a dashboard, number of activities per day is this much, and the expertise skilled workers are this much, in the sense automatically that can map, and it will say for each and every hour, each and every day, each and every month, how much resource are required to carry out this work. Okay, it will provide a pathway for proper planning of resource. At the same time, it will tell about the equipment. We all know about the optimization of machine utilization. There are many methods to optimize the machine utilization. Here, we see those things are done in offline. Okay, how much the machine is taking and how much output the machine is providing to other machine. Based on that, we were doing optimization those days. But now each and every machine is implemented with some sensors, data operation systems and measurement systems, and it takes the output and everything is consolidated. With the data, we come to know how much time the machine is idle, how much time is machine is working, and how we can optimize these cycles, the process, so that we can improve the machine utilization. Those things also can be automated with the help of AI. And then inventory management. Yes, inventory management in the sense we all know about the just-in-time concepts, Pokayoki, those concepts that those were evolved during 1990s in Japan. So those concepts can be effectively implemented with the help of this AI algorithms. We could predict the supply chain and inventory management. We could forecast the demand. For that demand, how much is the inventory required? What are the logistics arrangements required? All those things we can predict it adaptively. See, every week, every day, you come to know how much is fall in inventory, and maybe after 1 month, is it possible to meet it or not? Say if the lead time for the supply is 1 month, how you can optimize it properly. All those things can be managed with the help of the data which is available to us through the complete ERP system and the advanced algorithms applied in the manufacturing environment. Then the custom manufacturing is possible. See, previously we know that the mass production is basically for making a similar component, same component in n numbers, in 1000 numbers. Okay, so but now for each and everything we can change it. Say for example, in the machine tool, it's very difficult to change, difficult to print everything, right? But in a 3D printing, if you take metallic 3D printing, if you like to put your name in each and every equipment for identification, in the sense it's possible, right? Each and every product can be customized. Previously, it's very difficult for doing a tooling, changing, everything is difficult. But in the advanced manufacturing environment, it's easy to customize each and every product. Customization is possible. Okay, so then the generative designs, yes, I believe that there are many lectures provided on this part. The AI itself will create the models for us. The AI itself will provide different options to us. From there, we can start working. Recently, you could note that Autodesk has introduced one of the future where if you like to design a vehicle or bike or car, something like, you can take inspiration of 100 vehicles which are present in the market, and if you say in one click, you can combine, say the front side would be like this, tail side should be like this, something like some inspirations you can take, and with those inspiration, it can create a new design, new CAD model in few seconds will be available to you. From there, you can start working and you can improvise and you can build your own ideas and you can reframe the whole structure. Okay, you can tune that whole structure. So that's the kind of thing happening here. And how this design is helpful in the manufacturing. When the designs are generative, then automatically that provides options, immediate options for the manufacturing processes. We can generate the product sequences, process sequences, process optimization, tooling, all those plans we can generate with the help of AI implementation if the data is available to us. Okay. So this I've taken it. I think this white paper is available in open source. I take it from the IBM.com where they discussed about how this AI in manufacturing is changing the scenario in detail. Maybe for each and everything they have given the case study, and if you find it article, you please go through and you can get a very good idea on that. Okay. So any questions on this? Okay, so I will go to the next section where Yeah. So some use cases you can see here. You can ask me whether those algorithms are already applied in the industries or yet to be applied. Is it evolving? Those questions we may have in our mind. You can take it here. The PepsiCo uses AI-driven predictive maintenance, okay, for downtime optimization, for improving the production capacity, to reduce the unplanned downtime. How they are optimizing it, that they are doing through this AI-driven predictive maintenance algorithm. Okay, so the Airbus, they introduced generative AI for different alternatives of its aerodynamic structure. Okay, thereby they reduce the design time. They have generated various options. From there, they started doing it. Okay, so Procter, they introduced AI for quality control for the defect detection. Already many of the industries here in India also they implemented vision system. Slowly, AI built cameras also available in the market. Slowly the industry started using those cameras directly. See, we have face reduction algorithms in our mobile phone, right? When you take a camera and it will detect the face and it will say, and those features, no, those are kind of AI based algorithms that is improving the image processing, right? Similarly, cameras come with AI built kind of features. Sorry, is it visible? Prabhu, is it visible?
Yeah, sir, visible, sir.
Yeah, okay. So cameras come with some intelligence. Thereby directly you can use. No need to write kind of algorithms for image processing. Directly those algorithms are built in the camera. So directly you can use, and you could see that even in the security cameras we have some motion capture algorithms. So advanced kind of algorithms are available in the image processing side. And BMW, they introduced supply chain optimization for demand forecasting, for improving the efficiency. They used effectively. Siemens, they introduced robotics and automation for improving the manufacturing and the efficiency, precision in each and every process. Actually, they used fixed kind of programs. They were already having automation in place, robot in place, but with the help of the big data that is available to them throughout the factory, they have made that factory as a smart factory. They have integrated everything through this AI-based algorithms. And GE, they have implemented predictive maintenance algorithms, thereby they're improving the mission reliability. See, once if the machine is down for some time, say 1 hour or 2 hours, okay, if you take in automotive sector, for each and every minute, they may take 2 or 3 automotive products. Okay, so in each and every minute there may be a car coming out from the factory. So if that is the case, you just think about if one machine fails for 1 hour, how much will be the loss for each and every day. So in those cases, the predictive maintenance is playing a major role, and it could diagnose the fault in the machine. Just assume that, imagine that when we are in say the emergency room in the hospitals, they put many of the sensors, medical thing, the instruments, okay, for heartbeat measuring, BP, oximeters, everything they place, and there will be some buzzer sound, quite something would be there, right? You assume that everything is mounted on us in a shirt and we are moving and all the data is collected, and if there is a finding a fault, okay, in that, if it is giving alarm to us or if it is giving alarm to our caretaker, just assume that how it will look like. The similar kind of thing, the machines are made. So machines are constructed, built with many sensors, and those sensors are taking. Yeah, please. Yeah, so machines are mounted with many sensors, and they are acquiring the output, and those outputs are compiled, and some data analytics is done. From that, which is a faulty machine, or which is the faulty part in the machine, all those things are recognized, and it is giving some alarm or automatically it can call for the maintenance personnel to attend that problem. Those things is possible to do with this. That's what the GE has implemented, the predictive maintenance process. Thereby they're improving the equipment utilization, reliability, and reducing the downtime in the factories. Okay, so now I just like to give in academic interest. I know that many of them are the faculty members who are available here. With the academic interest, I would like to discuss on one problem, one case study on how the AI is implemented to optimize the process or to diagnose the machine. From the diagnostics, how the control is made with the help of another AI kind of algorithm. There are two parts. One is the monitoring algorithm, how it is used for modeling, and how it is used for controls. In those places, how we are making the machine as smart machine. That's what we are going to discuss. We all know that the predictive maintenance is basically uses sensor data, and before it fails, it gives the alarm or indication to us so that we can rectify that problem, right? So the traditional condition monitoring, even in the predictive maintenance, what is happening is up to predictive maintenance you can do just by seeing the data. That's the scope of traditional condition monitoring. Okay, so when you apply AI-based algorithms in that, the smart algorithms, that includes decision-making capabilities. Previously, that just shows the data, but here it can take a decision by itself. Sorry. Okay. Previously, the condition monitoring of machine tools or equipments or devices, those uses fixed models. They are manually configured. But AI-based monitoring is iterative adaptive models. Iterative adaptive model in the sense, if you are viewing one video in YouTube, okay, next day it is showing the relevant videos to you. It is actually learning your behavior. There is a AI algorithm behind that, right? If I play one song, Ilayaraja song today, tomorrow it will show another song to me in the same, maybe in the same year, what songs, no, those things it can show to us. It's basically a recommendation to us, right? So it's basically adaptive models that learns our behavior. We all know that the model, in the sense, it replicates the physical product. Okay, model in the sense it's basically in the form of equation, or maybe a pictorial representation or CAD model, or maybe a numerical a model that replicates the part, that reflects the part. So this is what we call it as model. Different models, analytical models. If it is an equation, we call it as analytical model, right? Analytical models. PV is equal to RT is basically analytical model. But there is a model, AI model. It does not have any equation, but it reads the behavior. You cannot model our behavior with the analytical equations, right? I cannot name someone and you modeling. Mathematically, it's not possible to model. But AI could model that because we have advanced algorithms that learns the behavior continuously, and it tries to predict what will be the next step. Okay, say when I'm seeing some songs or some images or some videos in the YouTube, okay, next day the relevant product is showing to me that do you want to purchase this in the Amazon or in some other website, right? So those recommendations are coming to us. In the sense, there is an interconnection in each and every apps, and they are continuously trying to learn our behavior, and they know that what I'm going to purchase tomorrow, what I'm interested in. Okay, so it will continuously show that product to us, and it will make attempt to purchase that product. That's how that algorithm is working. That's how they are using that algorithm, right? That is what we call it as iterative adaptive models. So it will improve itself. See, if I'm using the Google or YouTube or Facebook for 10 years, the model is completely tuned and that knows each and every step what I'm doing, which means that we are modeled. Our behavior is already modeled by those apps, right? If I'm using it for only 1 week or 2 weeks, okay, the model training data is less because the searches and what I'm interested in, all those things, the training data set, how much is available to that algorithm is very, very less. so that it is not able to predict my behavior properly. But if it is the same model I'm using, it same app, I'm using it in the same username for 10 years, easily it could predict what I'm interested in, what I'm going to do, what I'm going to purchase, what I will do, all those things it knows. What is my political aspirations, all those things it will be able to capture, and those are used by multiple people, right? So that's what we call it as iterative adaptive models. Okay, so in the traditional condition monitoring, the predictive maintenance, they are very moderate in nature and very often complex. But in AI models, interpretations would be very, very easy for us, because it will just give the data like a cake. It will present to you that there is a defect, there is a problem, you go and solve that problem. Such kind of direct information that will provide to us. So that's why interpretation part is taken care by the skilled people in the traditional monitoring that uses sensor, same data is available to us. But who will interpret that? Who will see that data? The person who is expert in that, handling those sensor data, he will see and he will conclude. But that part is taken care by the AI, and it will directly give you the result to you that this is the problem and you solve this. So that's what we call it as easy interpretation by the AI models. Accuracy of the model, yes, see, based on the expertise and based on the skill of the person, the decisions may vary. But when you train the AI, it will produce very high accuracy, and it will acquire the large amount of historical data and real-time data, and it will compare and take the decisions, which will produce a higher accuracy for us. Okay, skilled personnel are not always available to us to take decisions in the factory, but AI can be implemented. Thereby, no skilled persons are required to take or diagnose the data. Directly, the AI can give the interpretation of the data to us. Okay, so these are the various advantages of using AI. Okay, even in the traditional condition monitoring, we have the same components, same physical setup. There is no change in the hardware at all. The only thing is we are working with the data side. That's why in the initial lecture, in the initial stage itself, I mentioned that it is a data current. AI is basically a data current. So it is taking complete data and it is playing with the data, and it is providing different interpretations and forecasting prediction to us for taking decisions. Yeah. So this is about the condition monitoring. So in the data analysis, I told you, similarly, advanced algorithms, machine learning algorithms are used. Data classification, fault detection, easily you can do with the classification algorithms. Previously, that was with persons they are doing. Response time is very, very faster. Okay, within a fraction of a second, the algorithm will work and it will tell you. Okay, so we can devise very effective maintenance strategy, and adaptability of this one is very, very high. Say, for example, if you are using fixed models in the machine tools, okay, so those models will work up to some time. Once the machine started degrading, because each and every machine or equipment is subjected to wear and tear, right? The behavior will change. How a 12-year-old boy is running, okay, similarly a 60-year person cannot go, right? 60-year-old man cannot run, right? So the model differs with respect to the age of the machine, right? Similarly, when due to aging, how the machine performance is shifting, accordingly the AI can learn the behavior and it can tune the outputs, because in the new machine, if there is a fault, okay, easily it could identify. Okay, when there is a aging, then the tolerance, everything will shift towards some direction, right? Those things also the AI algorithms can learn, and it will easily adapt to those changes. So completely it will read, as I mentioned, how the Google reads our complete behavior. Similarly, the AI algorithms adaptively learns the behavior of the machine, accordingly that iterates the model completely. Yeah. So yeah, see, in the academic interest, as I mentioned, I would like to give one example how the drilling machine is converted into smart drilling machine by applying some AI-based algorithm. It's very, very vast subject, and one of my PhD scholar has completed her PhD in this, and I think the complete model and the complete architecture is available in the Journal of Measurements. I think you can refer to Elsevier Measurements Journal, where you can see that paper, adaptive drilling, hybrid adaptive drilling is the name of the title of that paper that you can go through. You can get all the details. Just I will touch upon how the complete mission is redefined as a smart mission than the conventional drilling mission. Okay, you all know about the drilling process. It is used for making holes, and there is a problem in drilling that when there is a problem in tool wear, okay, that will affect the surface quality of the component. Okay, so if the drill hole surface finish is not good, then it will affect the assembly performance. Okay, when you put a screw or nut or something like, or bearing, definitely it will affect the performance of the whole assembly. Okay, that's why the tool life is the one. Tool life in the sense that depends on how fast the tool worn out. Okay, if in the sense that much kind of cost we have to incur for that machining operation, for the drilling operation. So that is the only consumable that is available in the machine. So how well we are utilizing this machine tool, how we are extending the life of this drill bit. Okay, that much cost we can save. That is number one. Number two, while you are extending the life of the tool, how we are balancing the finish, surface finish of the drilled component. That is another parameter we have to see. These two are the main parameters in the machining. Then another thing, if you are not mounting the drill bit properly, okay, it will prone to run out in the sense out of axis. Okay, if your if the system is unbalanced, okay, what kind of behavior you will have? It's kind of wobbling motion you could see right now. So that's a kind of run out you could see, observe in the machine. So these are the three problems. First is the run out, how to sort out. Say when I'm mounting the drill bit, or from the automatic tool changer, if the tools picked by the CNC machine, and if there is a small picking error, okay, an insertion error that is leading to 0.2 or 0.3 mm run out in the sense, it will create some problem in the machine, and it will create so much of vibrations. And instead of having a perfect hole, say if you are taking 10 mm drill bit, the hole dimension would be around 10.5 or 11 mm. So that's how it will enlarge the drill hole. Okay, this is what will happen when we do with this. Okay, so the maximum allowable limits for the run out, the tool life, and surface finish are already defined. The standards, you are very well aware of the ASME standards. Okay, so in that they are clearly mentioned. Whether the machine tool is progressing within the limit or not, that we could analyze, and we can capture it, and we can maximize the tool life, we can improve the surface finish, and we can sort out the issue of run out. If there is a run out, machine should not work. Otherwise, it will spoil the tool. So these are the three objectives before to us to make the machine a smart one. Okay, so before going to this, in machining, how I can use this? I can use the AI for optimizing the tool path. Thereby, I can reduce the programming time, and I can reduce the machining time, and I can do the smart maintenance, predict the failures, and I can do the real-time adjustments parameters. Say if I am processing aluminum, okay, there would be some other parameters I should use. Okay, I can set. If it is a steel, that should be different. Is it possible to for the machine to identify this component when it is touching? Okay, that's possible. Okay, such kind of predictions and adjustments we can do automatically. The tool can adjust, machine tool can adjust by itself. Okay, and wear and tear prediction, as I told you. These things we can do with AI powered smart machining. In this, we are going to look after 2-3 parameters. Okay. So in this case study, one drilling machine is taken. So as I told you, the objective is to maximize the tool life, minimize the surface finish, in the sense improve the surface finish, and then avoid the run out. Run out in the initial stage itself we have to find out, and we need to avoid that run out so that we can save the component. Okay. So in this, what are the models I'm taking it? First, to model the problem in the machine tool, I'm taking two different parameters. One is the force, another one is the vibration. Okay. So in the force, there are frequency parameters. We call it as FFT, fast Fourier transformation. In that we take frequencies, and in the time domain analysis, we are taking how much is the peak to peak amplitude and RMS, those statistical parameters we are taking. So from this feature, frequency feature, we are doing SVM kind of algorithm, support vector machine algorithm. I don't have time to explain all those things, but you would have come across this algorithm. Support vector machine is algorithm that is used for modeling the runout. Modeling the runout in the sense, I'm just mapping the behavior of the runout. If it is a runout, how will be this force and vibration signals that I can find out through this AI model. Okay. So again, I'm using two more in this force and vibration signals. Okay, for predicting the roughness and the tool wear. Okay. Then I'm going for optimization with the help of another AI-based algorithm. I'm not going to discuss these things. So only just outline of these three models I would like to give. In this, what you can understand, how these two sensors, see, there is a physics behind this. If there is a tool wear, okay, if the tool is blunt, okay, that will take more amount of force to cut the material. Say, if you have a knife, okay, if the knife is sharp, you can apply less force so that you can cut it easily, right? If the knife is blunt, it's very difficult to apply the force. The same thing applies here also. If the tool is sharp, okay, easily it will cut. If the tool is blunt, if the tool has some wear in progress, so there will be some increase of force. That's what we are measuring it here. How the force is progressing, continuously we are monitoring. In the same time, if it is not cut and if the force is applied, what will happen? It will be converted into vibration or thermal energy. Say I have applied the force, because the tool is blunt, okay, so there is partially the component is cut. Then now what will happen to the remaining energy? That will be converted into some other form of energy. Vibration is one of the forms. So if the tool is blunt, by monitoring the vibration, I can say that there may be the problem in the tool. There is a problem in the tool with the wear part, which will be having this much, so that this much amount of vibration it is creating. This much amount of force it is consuming because of the blunt tool. Those things I can take it, for which I'm using AI-based algorithms. In this ANFIS, I assume that you are very well aware of this neural networks and fuzzy logic. So where it's a combination of, see, basically the neural networks takes the input and there are hidden layers, and it is basically adjusting the weightage function among the neurons, and it is producing the output to us, right? So we are combining this neural networks with the fuzzy logic. Is basically a fuzzy inference system is basically a classification algorithm, and combining both the things will give us the good idea on what ranges of data sets we can collect and how we can train it. Both advantages we can combine, and we can use these two algorithms to model the wear and the surface roughness. Okay, so if you take this is the basic experimental setup. It's a physical setup that is made one component, and then accelerometer, tool, dynamometer are fixed in this. There is a data acquisition system for tool as well as the vibration, and this is the overall setup. Accelerometer, tool dynamometers are used, and this is the drill bit 6 mm. This is a circular plate where we are going to make drilling, and when drilling started, the vibration and force signals are captured through this data acquisition system through some LabVIEW platform, and this is a workpiece material. Okay, this is drill tool. Okay, So these are sensor models. I'm not going in detail with that. Then see, for each and everything, say if there is a tool where, okay, we are going to take the vibration signals, how we validate that, how we cross-verify that. So for which some reference measurements we have to make. Once the tool is mounted in the CNC machine to measure the runout, okay. So junior plus presetter is the instrument that is used for measuring the runout of the instrument when it is placed in the CNC. Okay, so that we can measure it, and theoretically this is the reference value to me, and what is the corresponding vibration for this runout that I could measure. Circularity in the sense, if there is a runout wobbling issue, okay, it will create a oval like of shape rather than round shape, circular shape on the component, right? So I could measure it. Once if I find any problem in the runout, I can take that component, measure it with the vision system, thereby I can measure the circularity. These two are measured just to have a reference value for runout measurement. Okay, so drill wear, again we use the vision system to measure the drill wear, and then roughness, Taylor option subcoder is used for measuring the surface roughness. These are the reference instrument against which the vibration force parameters are correlated. Okay, so for example, this is the surface profile we get, and this is the experimental plan. Okay, so around 105 holes are made, 100 plus holes are made. In that the parameters are taken. Just I'm rushing it because of shortage of time. And what is done is runout model. So already I told you, I measured the runout conventionally through some gauges. Okay, I know what is the runout value. According to that, for that condition, how much, for the various runout condition, how much is the value of force and how much is the value of the vibration continuously occurred through the data acquisition system. That plot I have. So there are 100 different configurations of runout are induced. Okay, and observed that there is no, there is a progression in the runout, or how much is the runout and what is the corresponding vibration force signals. Okay, so maybe 15 to 16 experiments I could show here. Similarly, tool life also, different state of tools are taken. Okay, for against which what is the different force and vibration signals acquired, what are the frequency features of those things are derived, and conventionally the tool life is measured. No, those things are correlated. Similarly, for surface roughness, different surface roughness, what are the values of force and vibration, and the corresponding conventional measurement, those things are tabulated. As I mentioned you, this is what we call it as runout. You see here, there is out of axis. No, this because of this offset only, there is a oval shape comes in the component. Okay, so this is a typical vibration parameter that is taken, and this is the typical force value that is taken, and these are the conversion of time domain to frequency domain. You would have aware of the frequency domain transformation, fast Fourier transformation, and these are some of the experimental outputs where the peaks are coming. Okay, so just this for information. And what we are doing here is those number of each and every measurement we have lakhs and lakhs of output. They are directly given to the vibration. They are directly given to the least square SVM model and ANFIS models for training and validation. Okay, so you can see here these things are validated. Those, I think these are not required. Okay, so why we use this? See, basically there are many type of AI based algorithms are available. SVM is one of the classification algorithms. Okay, so that we use it for differentiating the component, that is for image recognition, text categorization, bioinformatics, all those things we can use it. Basically, if you have say if you have two colors, there is a plane here, no? So that is basically a line, okay, that's created by SVM algorithm, okay, with the given data set, and it will classify that this is something different data set and this is something different data set. Okay, so if you are having apple and orange, okay, that is put it, okay, outside, there are 100 such apple and orange are there. And if you take a photograph, it will classify that these are oranges and these are apples. Something like, for such kind of thing, they're using this SVM algorithm. Okay. So for SVM algorithm, comparatively, when comparing with the neural network, less amount of data set is sufficient. That's why that is got selected, because inducing a fault in the machine tool is very, very difficult. Changes are very, very difficult, right? So this is basically a runout model that is using this LSSVM. Speed feed are the inputs and their vibration force measurements are input for that. And there is a model, AI model, that predicts a runout. Okay. And you can see how the outputs are trained. Different discrete, different experimental things are taken and it is measured with this, and this is the predicted output. AI predicts the runout. Say if this is the vibration and this is the force, and the runout would be this. Okay, you can see the red line is the predicted output and the blue line is the actual runout. So you can see a very close correlation between the AI predicted output and the measured output. Okay. Similarly, for toolware also, the same kind of models are developed. As I mentioned, there is neural network and FIS based algorithm. ANFIS is modeled, and here also you can see how the parameters are configured, and finally the training data set and these things. If you take, there is a close correlation between these two checking points. So the model accuracy is about 93%. Yeah. So with this, the overall adaptive control strategy is implemented in the machine. So it's basically taking these models, and accordingly it is controlling the overall process. Once this LSSVM model says that there is no run out, it will start measuring the roughness, and if roughness is within the range, it will start measuring the tool life. Okay, and if roughness is within the range, it tries to optimize the tool wear. If the tool wear is in optimized range, it will try to adjust, reduce the roughness, thereby it will improve the surface quality. So this is how I don't have time to explain this one. The complete algorithm is written and simulated where how these three different areas, the runout is one area that is separately modeled with one AI algorithm. Roughness is one area, one parameter that is separately modeled, and tool wear is another parameter that is separately modeled. How these things are combined to achieve the core value of the optimization, right? Improve the tool life for better economics, tool economics, okay, machining economics, and for better finish, for improving the quality of the component, how to improve that. So the complete strategy is arrived and that's got implemented. Okay. So in the implementation, you can see here, see the machine is not working in one set of conditions. It is altering the speed and feed of the machine with the input of tool life and surface finish. Okay. So you can see here how it is altering the speed and feed, thereby you can improve the tool life and the surface finish. Okay. Those things you can see it here. So with this, maybe it's very difficult to understand all the things. Maybe you can see this this paper. Okay, measurement, the general measurement you can see, find out, and you could see how the approach is done and how that is got implemented clearly. Okay, so what I'm trying to say is in high level, I talked about the inventory management, right? In AI implementation, I talked about inventory management, supply chain, digital twins, all those things. In the predictive maintenance, we can identify the machine's fault and breakdown, and we can analyze those things, right? In that, how we can adjust the parameters by itself. Okay, that is what I explained to you. So there are many layers of implementation of AI. In the factory level, overall data analytics, we can use it. Okay, in next level, integration level, we can use it. In inventory, ordering, purchase, that level, macro level, we can implement the AI. And in machine level, you can apply AI. Overall mission productivity, we can apply AI. And parameter adjustment, how we can adjust the parameter, thereby optimize the machine. That also you can apply the AI. Okay, so you can deepen the technology and you can go in detail in micro level, and everywhere you can apply this one, and vertically you can integrate all those things. So it is, we applied the AI algorithms in the machine tool for optimization. Okay, tool optimization and quality optimization, and then this can be combined with the machine tool utilization algorithm, and that can be combined with the inventory management, resource management, machine utilization kind of thing, and this can be combined with power management, thereby how you can reduce the power in the machines when it is in idle condition. That can be linked. So this is how vertically you can link these models to achieve the overall objectives effectively. Okay, so I think with this I would like to stop, and the time is already 8:30, and I don't know how you are convenient with this time, because I know the teaching morning to evening after working hours you are attending this session. I could understand the problems what you have in listening this lengthy lectures, and many sessions are scheduled evening, right? Okay, so with this I would like to wind up, and the floor is open for questions. If you have any questions, you can ask.
Participant may ask question.
Hi, hello, Dr. Dinakaran. This is Babu.
Yes, please. Yes, Babu.
Yeah, I saw your PhD report, and it looks very interesting. One, so since you used the CNC machines, I'm working with a few of the SMEs in India where they have the conventional machine. Okay, so we are having a very difficulty in placing the positions to measure the main components of measurement is a vibration and vibration. So we have a very difficulty in positioning the sensor. So how did you manage? Yeah. So.
Regarding this positioning, see what we are aiming at. That's very sensor mounting itself is a separate study.
Yes. Yeah.
Sensor mounting itself is a very difficult thing, because what parameter we are aiming at, accordingly we have to place. Say if you are focusing on the tool, the placement should be different. If you are focusing on the feed motors failure, you have to present it, position it properly in different place. If you are focusing on the speed actuator, that motor, actuation in the sense, is there any problem in the motor? If you like to monitor that, you can do that. If you like to monitor the backlash, so we have to place it in a different position. So different. What is your focus? What problem you are going to address from the sensors? What you are going to acquire, and what is your objective, or what problem you try to optimize? That based on that, the mounting of sensor varies.
Yeah, that's one of the real challenges we faced actually.
Yes.
Apart from that, I'm asking about this one on the Indian market actually. Like when you work on Western countries, we don't have any issues like when you did on the image recognition and condition monitoring, right?
Yeah.
So we don't have any issues like any condition monitoring, right? Most of the, if you're doing any image processing, it needs high resolution cameras, right? So you know the high resolution cameras runs into a single camera runs in between 5 lakhs to 20 lakhs. Yeah. So like when we worked with one of the SMEs, we just went to the project proposal, everything. And the final stage, the thing came up was like they need 3 cameras, which cost them 25 lakhs. Instead of that, like countries like India, we have an low-cost country, right? So management always thinks about the IRR, right? The rate of return is the main objective of them. Any investment is made. So they said that instead of investing a total of budget of 50 lakhs, it's better to hire a person and look after the things manually, right? So how do you feel the challenge is going to be Like when India is adopting this Industry 4.0.
Yeah, see, always there is a break even, as you mentioned. Okay, always there is a break even. See, there is a act called Prevention of Manual Scavenging. Okay, in 2013, that's passed by Indian Parliament. But still, people are going in the sewage, and every day we are we are losing our lives of our people, right? Though there is a mandatory rules and regulations, laws are there. Okay, there is no break even between the cost and the machineries. That's why this problem arises. Okay, see, if the sewage cleaning machine is available for 10,000 rupees or 5,000 rupees, everybody will buy and use that. But if the sewage cleaning robot cost is 10 lakhs or 15 lakhs, and if the person who is coming and cleaning just charging 800 rupees or 1,000 rupees, okay, people or society will go for this only. Okay, there is a huge difference between these two, right? The same applies to here also. If there are differences, see, if the investment is very, very higher, definitely people will hesitate to invest on that. But I think there are some low-cost solutions available for this one, how much the solution you want, and there are some low-cost solutions. We can play with some algorithms, that way we can bring some compensations. Okay, within some boundaries we can play. Maybe if you're looking for very high-end cameras, the cost would be around 3 lakhs, 4 lakhs or 5 lakhs. Okay. See, for example, one of the projects that we are currently doing is just surgical instrument performance monitoring. In that we are using normal webcam. Okay. That itself solves the problem.
Yeah.
Okay. It's just a simple camera, is cost around 2,000, 2,500 rupees. That's available in the market. Okay, that solves the problem. Just I would like to measure the opening angle of the jaw of the instrument. Okay, that's easy to measure that one. So what problem we are attacking, and what would be the, sometimes our people will overdo that.
Yeah.
Okay, so by seeing that problem, and which would be, see, just because we are trying to solve that problem, it should not be a high-tech thing. Okay, it may be a low-cost solution. It may be a very simple solution also. So we have to find out some alternatives for that. But the imaging things are, I think, very low-cost systems are available in the market. You can revisit that proposal, Babu. Maybe even I can also help you. Say, maybe what kind of system you are looking for, and what is the accuracy, resolution, all those things.
No, I think it is a sheet metal factory. You know that sheet metals are getting manufactured at a high speed, so we need a high resolution, high speed camera.
Oh, high speed camera. Okay.
That's totally not possible with these low resolution cameras.
Low resolution cameras. Okay. Okay.
Yeah. So I think
there is a deadlock. There are bottlenecks in each and every technology, but slowly it is picking up. Slowly it is picking up. So previously we did not see any robots used by MSMEs.
Yeah.
But if you come to Chennai and in Perungudi, different places, different zip cards, and each and every MSME companies, they have a welding robots with them, because finding people for that one is very, very difficult for them. Okay.
True, that's true.
So robot, so slowly it's picking up. When the market is expanding, proportionally the price of those equipments and advanced things also will fall, right?
Yeah, true.
Yeah. So because of mass production.
Yeah, I was really interested. Like when I think when we are in the university, right? So my first presentation was on low cost automation, which was correctly described, pulled out from the journal paper from IIT Bombay, where they had a specialized team on a low cost automation. Still, they have a specialized department focused on low cost automation for SMEs that mainly serves on regions across Maharashtra. When I was talking to some of the IAS officers when I was last time, how about setting up this low-cost design center in the universities, because that helps a lot of SMEs. Right? So when you go for implementing this Industry 4.0, so most of our Indian industries are into the level of Industry 1.0 or 1.2 level. They are not even came to the 3.0, like, so most of the conventional engineering shops are made with a conventional lathe and conventional drilling machine. They don't even have the CNC machines. So, which is going to be a drastic challenge for the government when they are moving to the Industry 4.0 readiness. So that's since you are also part of many academic advisors, I think it's one of the things which you can emphasize universities to set up in low-cost design centers. SMEs can benefit, right? So even this kind of advanced solutions, like for OEMs, is not a problem because they are handled with, they had so much of huge money, so it's not a problem for them. It's in terms of SMEs, so they're always concerned with the money.
See, definitely. See, in India, there is a problem with MSMEs in setting up R&D centers because they are struggling to run on daily basis itself.
Yes,
they are running like anything. But how do they set the research centers and how they carry out the research or how they develop those process equipments, all those things? That's very, very difficult. So that area of the academic institutes, as you mentioned, in Europe and US, all the research and this kind of designs are happening in the universities and that are translated to industries, right?
Yeah.
There is a huge gap here that the academia and the industries are not working together. They are in silos and there is a kind of isolation barrier between these two. Not understanding it properly, or the expertise are not visiting industries, or there is some confidence level is missing, right, between these two parties. So I think the huge demand that is happening in the manufacturing sector at a high level, I think that will solve these problems. That's what I assume, because unless we get some orders, and you'd say if some OEMs are coming to Chennai, in the sense, say for example, if any automotive OEM is coming, then in and around there may be many of small scale companies, there'll be supplier for them. No, so like this, how that manufacturing sector is improving as a whole, that will bring the change in the bottom line.
True, that's true. No, the thing is, like, since India, we have so much of SMEs to have an attain Industry 4.0, we need a holistic development and not a concentrated development, right? That's the one thing. So that the university has to work with the SMEs because.
Definitely. I agree with your point that people should come forward to work with industries. And that bridging, that should come from, that initiative should come from both the sides, both from industry as well as from academia. There should be a regular tie-up, and they should believe the academic institutes. Many bright people are there, experts are there in the academics, but they are not utilized fully. That's the unfortunate thing that we have. The industry, they feel that it's waste of time to engage academic people because of their delay in process, or that their routine is different. No, that's the issue with industries. We are running within the time. They have targets and they have timelines. They have milestones. Okay, that chart only before them. They don't see the academic institutes come together with these milestones. That's the issue. But academic institutes also should understand the need of industries, not only with respect to the technology, also with respect to the management aspects like the timelines and targets. So that's what it's. I think it's a very long-term process that will take some time, but I think slowly that is picking up.
True. That's true.
Thanks,
Dinakaran.
Thanks.
Got my time to attend your presentation just since I was into, that.
I think yours is over.
So, mine is over yesterday.
I think it's. I missed that. I missed you.
I just covered mostly related to, I was mostly my domain into automotive, so mostly covered a little bit on
automotive thing. Okay.
So I just given the overview because my job is very easy, right? So it's like first days is going to be fundamentals, and then yours is going to be a specialized one. So getting into AI.
Yeah.
And to to take this AI into the production level, we need a lot of production data, real-time data. That's going to be challenging actually. So even to put it the point into manufacturing, like see, as Dr. Dinakaran said, the most of the Western countries, the research is goes from universities to industries. Like so, here in UK and US, they've done it, and one more project they've done it is like Factory 2050, which is nothing but a manless factory. So I just visited an advanced manufacturing research institute. They set up advanced manufacturing facility.
Is that at Coventry University?
No, it is in the University of Sheffield. They have an advanced manufacturing.
Okay. So they have a similar center.
Yeah.
They have a similar center. Yeah.
So they have already the dream of 2050 was into plan. So the factory runs automatically, so it can be controlled remotely. A person sitting in India or in China, anybody can support it. So nobody need to be there in the hazardous environment or nuclear or automotive. There's no need to be there. It's a very interesting thing. The challenging is like on the cybersecurity side, they are working on it because every systems are interconnected. There is somebody can hack to your factory and stop it, right? That's a major concern. They're working it out. So I think we have another 25 years to go. So I think that's a major thing.
Okay.
Yeah. Thanks, it's a nice
presentation. Nice. Yes. Thanks.
I had an opportunity to see your projects, PhD projects. Yeah, this is the time I spent.
No, it's one of the PhD topics of my PhD candidate. Yeah.
Yes. I'm done, Dr. Dinakaran. Thank you.
Yeah, thank you. So any other questions? Otherwise, we'll wind up. Prabhu, I think there is no more questions.
Okay, sir.
Once again, I would like to thank all of you for giving this opportunity. Thank you.
Thank you, sir, for your valuable speech towards this topic, sir.
Yeah. Thank you.
Thank you, sir.
Thank you.
Thanks.
Okay, participant can fill the feedback form and after leaving the session. Before leaving, you have to fill the Google form. I will post the Google form in your chat box.